Hello everyone, I hope you are doing great. Today I'm going to discuss about drilling hydraulic. The audience of this unit are the student in third year, second semester. And at the end of this lecture, a student will be able to find the optimum nozzle size of the bit. The application of drilling hydraulic is that it will be helpful for the hole cleaning and safe mud weight window. So for this part, we will be able to find a sufficient amount of flow rate to carry the cutting to the surface. And also it's another part for the well control. The bottom hole pressure should not exceed the fracture pressure of the formation. And of course it's a bit nozzle selection, that we can select the nozzle size to maximize the eroding action of the fluid, and also for the rig selection, for the pump selection, also for pump specification, what kind of pump specification we should have for this purpose. Before continuing, let me show one YouTube video to have a look on the different part of the drill string and on different part of the drilling that we have. Look at here, the mud is passing through the drill string, which is drill pipe and the drill collar, and it will come out from the bit nozzles. That here we have the bit nozzles. After that, it will carry the cutting from the face of the bit to the annulus and then finally to the surface. So we can see that the passage is from the pump through the surface equipment, drill string, and then the bit, and then the annulus, and then after that it would be the share shaker. Therefore, if I want to discuss about it, I can say that from the pump pressure, if I have the pump pressure here, then it has to pass through the drill string, which consists of the drill pipe, drill collar, and then after that the bit, and also the annulus opposite drill collar and the annulus opposite the drill pipe. So if I want to write the pressure drop for the pump, it will be equal to the pressure drop due to the friction plus the pressure drop in the bit. But what are the friction pressure drop? It's the pressure drop in the drill pipe, drill collar, and in the annulus opposite the drill pipe and drill collar. And as we have discussed before in other sections, in order to find the delta PF, or the frictional pressure drop, we need to find the C and M in this power law equation that we have. And how actually we can find this C and M is that because we have two unknown, we need two equations also. How we can do that is we have to give two different flow rate and have to find the delta PF, then we can find C and M. But usually how we can do that, these two different flow rate is one of them is close to the minimum required to lift the cuttings, and the other one is close to the expected flow rate to be used for the next bit run. If we do that, we can find, so if I find the first flow rate, then using the flow rate I can find the pump pressure, and using this equation that I have over here I can find the bit pressure. When I have the bit pressure and I have the surface, because the pump is at the surface, so I can find the pump pressure. So if I find this bit and this delta P pump, I will be able to find delta PF. Therefore, in this equation I will have delta PF and Q for the first step. The second one I will have another flow rate and I can find the delta PF. When I have these two, I will be able to find the C and M. That's how it's working. Let's go back to our slides. As we just mentioned, the pump pressure can be calculated from the passing through the drill string, which is drill pipe, drill color, bead, and the annulus area. And what about if I have a downhole motor? If I have a downhole motor, then what is happening is that I will have another pressure drop due to the downhole motor that I have to add it here. So as we just mentioned in the one note also, we can simplify this equation by considering a delta PF, which delta PF is the total pressure drop due to friction. Everything that I have except the pressure drop in the bead. I also can write the pump hydraulic horsepower in the same way. So the pump hydraulic power would be equal to the frictional hydraulic power and the bead hydraulic horsepower. So in order to find the bead pressure drop, I just need to write the Bernoulli equation from point A to point B. So after that I would be able to find this equation for the pressure drop in the bead. In this equation I have a rho, which this rho is the mud weight, the Q which is the flow rate, and CD discharge coefficient is unitless, and usually the value is between 95 to 0.98, and I have a total nozzle area, which the unit is in a square inch. The unit for the flow rate is GPM, and for the density is ppg. This constant that I have here is to convert units in PSI for the field unit. Another parameter that we need to find is the jet impact force. The equation for the jet impact force is given here, which has a CD, rho, Q, and then delta PB, which we explained about all of these parameters before. Another equation that we need to know is the hydraulic horsepower. The hydraulic horsepower is equal to the pressure drop in the bead multiplied by the flow rate divided by this constant value. To convert the PSI and the flow rate to hydraulic horsepower. The flow rate, it should be this one, GPM. Gallon per minute. It can't be ppg. And another one is the jet impact force that we just discussed about how we can find the jet impact force, and the unit is pound, of course. So we discussed about this equation also, and how we can find the C and M. Actually, we have to give two flow rate, and in these two flow rate we have to find the delta P pump, and using the equation of the pressure drop in the bead that we just discussed about it here, I would be able to find delta PF. So I will find delta PP, delta P bead, so I can find delta PF. I have two flow rates, so I can do it for 2 times and find 2 different delta PF. So let's go through this example that we have here. 2 circulation tests have been performed where the pump pressure has the pressure of 2500 and 1850 and recorded the flow rate of 300 GPM and 180 GPM. If the bead has 3 nozzles with all numbers 13, predict the pump pressure at flow rate of 250 GPM. and discharge coefficient CD is 0.95. The breathing fluid density rho is 10 ppg. When we are saying the nozzle number is 13, actually we mean, what it means is that it's 13 divided by 32. It's not actually the 13, because we are reporting the nozzle size in the base of 1 divided by 32. So when it says 13, it's actually 13 divided by 32. So if I use this equation, pi divided by 4 multiplied by di divided by 32 to the power of 2, I would be able to find the area of each nozzle. And if I add all of them together, so I can find the total nozzle area. So the first step was to find the total nozzle area having 3 nozzles, and all of them had the same nozzle size. Not all the time the nozzle size will be the same. Next, because I have the flow rate, I have the density, discharge coefficient is given, total nozzle area also be found, so we would be able to find the pressure drop in the bead, delta P bead. We can find it for the first flow rate. For the second flow rate, which is 180, also if we use this equation, we can find the pressure drop in the bead. And the pump pressure was given in the question, so we can find that. What we can find, having these two, using this equation over here, I can find delta PF. So because I have 2 flow rate and 2 delta PF, I would be able, if I just substitute it in this equation, then I would be able to find C and M. If I divide them together, then I can cancel this 2C, and easily by getting one logarithm I will be able to find M. And if I find M, I just need to substitute it in one of these 2 equations to find C. That's nothing fancy about it. You can just skip this part. And that's all that we needed to know about that question. And then now nozzle size optimization, and how we can actually optimize the nozzle size. There are 2 different methods that we can optimize the nozzle size. One of them is the maximum jet impact force, and the other one is the maximum hydraulic horsepower. And then the things that I want to mention here is that these 2 methods are very similar, and the final answer, if one of them is in the maximum, the other one would be in the 90% of the maximum. So it doesn't really matter which method we are using. But how we have to find this nozzle size, it's actually explained here. So the first step, as we just gone through it, it was finding C and M and having this equation of delta PF. When I have that one, then I will have 2 different equation, which, let me explain it here before moving there. So the first method is that maximum jet impact force. So to have the maximum jet impact force, this Fj should be maximum. And how it can be maximum is that dFj divided by dq is the derivative. The first derivative equal to 0 should be maximum. So if I do that, and if I consider the delta PF as C Q to the power of M, what I can find is this equation. So whenever they are asking us that the maximum jet impact force is the method for the nozzle size optimization, we have to use this equation. And whenever they are telling us that the maximum with hydraulic horsepower is the method that we have to use, the only difference is that because we are using different equation to find this equation of m divided by m plus 1, it would be slightly different with what we have here. Here it's m divided by m plus 2. Here in the maximum bit hydraulic horsepower is m divided by m plus 1 multiplied by the pressure drop in the pump. So that's all. That's the only difference. The rest, it will be the same. So let's go back here, then I can explain the procedure to find the nozzle size. The first step is to decide which equation I want to use. Is that the first equation over here, this equation, or the second one, based on the method that we want to use. After finding the pressure drop in the bead, because in the question the pump pressure will be given, then we have to find the bead pressure drop using this equation or this equation. So when I have the pressure drop in the bead, and I can calculate the pressure drop, frictional pressure drop, therefore I would be able to find the frictional pressure drop, because I have the pressure drop in the bead and I have the pump pressure, so I can find the frictional pressure. When I have the frictional pressure using this equation, because we found C and M before, I would be able to find the optimum flow rate. And when I have the optimum flow rate, I would be able to find the total nozzle area. So one more time, the first step is to use one of these two equations based on the method that we want to follow. The second step is that I have the pump pressure, I have the pressure drop in the bead, so I can find delta PF. When I have delta PF, I can find the flow rate, optimum flow rate using this equation, because I found C and M before. And when I have this optimum flow rate, so I can find the AT or total nozzle area, because in this equation also I have found the delta P bead, I found the optimum flow rate, I have the mud weight, CD is given, the only unknown is AT that I need to find. Let's look at this example over here that we have. Optimize the bead nozzle size based on both criterion of the maximum jet impact force and the maximum hydraulic horsepower across the bead. The circulation test suggests that parasitic pressure can be characterized by the PF equal to 250 multiplied by the flow rate to the power of 0.35. The pump pressure is expected to be 2800 psi and the mud weight is 12.5 ppg. ppg is pound per gallon, and discharge coefficient can be assumed as 0.98. So as I just mentioned, the first step is to find the pressure drop in the bead. So I have M is 0.35 based on this equation. In this example, for simplicity, we have given C and M, so we don't need to calculate that separately. So M is 0.35. If I use the equation, I can find the pressure drop in the bead. I know how much is the pump pressure, I can find delta PF. When I have delta PF, I can find the optimum flow rate. And when I find the optimum flow rate, I would be able to find the total nozzle area using this method. So the flow rate is 422 and the total nozzle area is 0.515. The next one, so if I have the total nozzle area, then I have to find each nozzle size. If I consider each one of them to be 15 divided by 32, it would be something near to the total nozzle size that I have. The next method is M divided by M plus 2. If I do that, delta PF would be 2383, and from here the optimum flow rate is 627.5, and the total nozzle area is 1.01 square inch. And what nozzle size can give me this total nozzle area is actually 21 divided by 32. To find this value of the nozzle size, what we have to do is to try and error. With try and error, you will be able to find it. Usually that would be the end of this small chapter that I have discussed about it. So I have prepared for all the sessions at least one Socrative quiz during the session that I will check the understanding of my students, or it can be used for a student to check their knowledge before coming to the class. So for example, for this drilling hydraulic that we just gone through it, I have provided before like 5 questions that I guess only this one you will be able to answer. The parasitic pressure is 1000 psi, while the pressure across the bit is 400 psi. How much is the pump pressure? So if we look back to the equations that we had, it's here. So what we need to find: parasitic pressure 1000, pressure across bead is 400. How much is the pump pressure? Yeah, how much is the pump pressure? So if we just add them together, it would be 1400. That won't be the way that the student will see the questions. Just here I want to show how I have created this part to check the knowledge of my student during class. So here I have provided 5 questions. As you can see, I have like 30 to 40 set of the question that during the class it can be sometimes 1 or 2 hours or maybe 3 times to check the knowledge of my student, to make sure they have understand everything. Thank you so much for listening.